In this lab, we used the variational method to calculate Hartree-Fock values for the ground state energy of helium and other helium-like atoms. Particular parameters were solved for at this ground state, and then they were used to calculate the first and second ionization energy levels and the nuclear effective charge for each electron in both helium and the other helium-like atoms.
The Hamiltonian operator for our helium-like atom is represented here in equation 1. In order to find the ground state energy, we have to introduce our variational parameter here, and equation 1 can be rewritten to equation 2 with our variational parameter. So in order to calculate the expectation value of the Hamiltonian operator given in equation 2, we need to use spatial integrations to find the expectation value for each term within our Hamiltonian operator. So in order to do that, we take it, we're going to work with the first two terms. We want to find the expectation value of the first two terms. So right here is the expectation value equation for a Hamiltonian operator. And by this criteria, where a Hamiltonian operator operating on a wave function equals the energy times that wave function, we can substitute in energy for this Hamiltonian operator within the expectation value equation. And since this is a scalar quantity, we can take it out of the integral, and the wave function times its complex conjugate, the integral of that equals 1 if they are the same right here. Therefore, the Hamiltonian operator equals the energy value. And for the main objective of this experiment, we're trying to find the ground state energy of a helium-like atom. So in order to do that, we want the ground state energy with the expectation value of each of the 5 terms. So it's a sum of each of the 5 terms from the Hamiltonian operator. Therefore, we have just found the first 2 terms of the ground state energy, it being from the first Hamiltonian operator and the second Hamiltonian operator, and those two equal each other since it is in its ground state, and that value is represented here. So in order to calculate the expectation value for both V1 and V2, or that is the objective right now. So the equation for both of these terms is c minus z e squared over r. So in order to solve for this function, we need to use the virial theorem in order to help us solve for it. So the virial theorem is 2 times kinetic energy equals B times the potential energy, where the potential energy is A x to B. So our potential energy operator is represented here, negative c e squared r to the negative 1. Therefore B is negative 1, and kinetic energy is negative 1/2 potential energy. So in order to find the ground state energy, it is equal to the kinetic energy plus the potential energy. Subbing in what we solved for the kinetic energy here, we found that the 2 times the energy equals the potential energy operator. And the subbing in what we have here for the potential energy operator, we find that 2 times energy equals our potential energy operator. Now, we will use this in order to help us solve for our equation over here. So over here, what we want to do is we want to substitute in 2 times the energy, because we want to find the energy. So what we have to do is we have to put in a factor of our variational parameter in both the numerator and the denominator in order to factor out 2 times the energy. So once we do that, we can then substitute in what the actual energy function is into our equation, and we end up with finding that for both V1 and V2, this is what the expectation value equation is for those 2 terms.
So next we wanted to calculate the expectation value of our Hamiltonian operator. So just to remind you, this is our operator up here, and these are the values. Each three of these are the values for the spatial integration of each term. Since H1 and H2 are the same, we get 2 of them down here, so 2 times this integration. And since our 2 potential energy terms, V1, V2 are the same, we get 2 times this term. And then finally, the electron repulsion term, the interaction between the 2 electrons, we get this term right here. This is our expectation value for our energy in the ground state. And in order to find it, we simplify it to this equation right here, because we take n is equal to 1, and we pull out the e squared over a because it's simply a unit in the Hartree-Fock method. So this is our initial equation, and then we simplify it down to this, and we get Zeke squared minus 2z Zeke plus 5/8 Zeke. In order to solve for the ground state energy, we need to minimize the expectation value with respect to Zeke's, and we do that by taking the derivative of this equation and setting it equal to 0, as we show right here. So once we've minimized our energy value here and set it equal to 0, we solve for the variational parameter Zeke's as a function of z. Here we get z minus 5/16. We then plug this expression back into our initial expectation energy value equation up here. So we plug in z minus 5/16 for Zeke's in each instance up here. Once you do that, that equation simplifies down to equation 6, and our energy equals negative z minus 5/16 squared. Then to solve for each ground state energy, we simply plugged in the atomic number for each atom. And for helium, we got negative 2.847, which is 1.93% accurate. For lithium, we got negative 7.226, which was 0.786% accurate. For beryllium, we got negative 13.597, which is 0.424% accurate. And for hydrogen minus, we got negative 0.4727 Hartrees, and that was 10.141% accurate. All the above values were also in Hartrees.
The next part of this lab deals with ionization energy. We were to calculate the first and second ionization energies for a given set of atoms. So the equation for ionization energy is given here, where E sub n, the energy, equals this given equation right here. Now the energy right here is in Hartrees. So in order to convert from Hartrees to joules per atoms, these get converted, and the final equation is this right here, because the principal quantum number for each of the atoms that we're dealing with is 1 because it's in its ground state. So the total ionization energy equals I times the nuclear charge squared, where I is 2.178 times 10 to the negative 18 joules per atom. Now, in order to convert from joules per atom into kilojoules per mole, we have to first multiply by Avogadro's number. That'll give us joules per mole, and then we have to divide by 1,000 in order to get kilojoules per mole. Now, this can be applied for the second ionization energy only. For the first ionization energy, it is a little different due to the shielding effect of the first electron by the second electron. The second electron shields the first electron from the full charge of the nucleus. Therefore, the effective nuclear charge that is experienced by the first electron is the principal quantum number minus, the nuclear charge minus sigma, the shielding constant. That's how much the first electron is being shielded by the second electron. Therefore, the ionization energy for the first electron is I times the quantity squared of Z minus sigma times Avogadro's number divided by 1,000. In this part of the lab, we were to find the first and second ionization energies of helium, lithium plus, beryllium 2 plus, and hydrogen minus. So in order to find the first ionization energy, we have our general equation that we solved for previously. In this, we need to calculate the shielding constant for each of these atoms. So in order to do that, you have to write the electron configuration of each of these atoms. And as you can see, they are all 1s2. Now the shielding constant is the sum of the electrons in their respective orbitals. So for a 1s orbital, the value of 1s is 0.3. Since we have two 1s orbital electrons, the shielding constant equals 0.6. Now plugging that in for sigma in our general equation up here, we find that for each of these atoms, this is the first ionization energy equation. Now all we have to do is plug in or substitute in the nuclear charge for each of these atoms, and we find the first ionization energies of each respective atom. Now for the second ionization energy, we can use the simpler equation that we solved for previously, and all we have to do is substitute in the nuclear charge for each of these atoms, and this gives us the second ionization energies for each respective atom. And these values that we solved here were within 5% of the accepted ionization energies for each of these atoms.
The final portion of this lab dealt with answering some questions based on what we analyzed. The first question is, what prevents your calculation from having exact agreement with the experimental values? The reason our values were a few percentage points different than the actual experimental values is because the variational method is simply an approximation used by minimizing a variational parameter. Additionally, certain assumptions using effective nuclear charge and the constant used to find effective nuclear charge are just an approximation, not an exact value. Finally, the Schrödinger equation can only be solved exactly for a hydrogen atom which has one electron and one proton. The atoms dealt with in this lab had 2 protons and 2 electrons, which makes it more complicated, and the Schrödinger equation can't be solved exactly. The second question, which atom or ion, helium, lithium plus, beryllium 2 plus, or hydrogen minus, will lose an electron most easily? The answer to this question is hydrogen minus, simply from the analysis of ionization energies earlier in the lab. The first ionization energy of hydrogen minus is the smallest, therefore it is the easiest to remove an electron. The third question, what are the ground state electronic configurations for the various atoms that we researched? The answer is all the same and is 1s2, simply because they all have 2 electrons. The fourth question, what is the effective nuclear charge experienced by each electron in helium? This goes back to the study of effective nuclear charge we mentioned earlier. We use our equation for effective nuclear charge as the atomic number minus the constant, the effective nuclear charge constant. Calculating that, Z minus 0.6, Z is 2 for 2 protons, equals 1.4. That's for the first electron, and this would be expected to be less than 2 because this first electron is under the effects of shielding from the other electron. The second electron is just simply 2, and it's getting the full force from the nucleus because there is no shielding. Finally, the fifth question, is the total wavelength in the following equation normalized? The answer is yes, it is normalized. The normalization constant for this particular equation is 1 over the square root of 2, and this can be proven in this various calculation where the normalization constant squared times the integral of the complex conjugate of the wave function times the wave function will equal 1. Here's the reference we used throughout this lab. This production was brought to you by the PChem warriors. And remember, an operator must always act on a function.